So in this session, we are going to discuss the next toy problem, that is the 8% problem. It is one of the most classical and elegant problems used in AI. So you might think that what is this 8% problem doing here, starting from 1870 till with this cutting edge AI technologies. So the 8 puzzle teaches us how intelligent agent thinks, searches for a solution, and it makes the decision. So what we will cover here is we will just brush up the difference between toy and real world problem, and then we'll go into the 8 puzzle problem. We will talk about its components, state space, and solution methods, and then we'll do a small comparison on the algorithms. Okay, so the difference given here with respect to toy problem and real world problems. So toy problems are generally intentionally designed because the rules are stated exactly, the boundaries are defined clearly, there is no ambiguity. So it is basically designed for a fun purpose or educational purpose. So when you talk about the real world problems, people really care about solving this real world problem. Any problem, a medical diagnosis, route finding problem, weather forecasting, financial forecasting. So it is more complexity, not only the complexity. So there is no proper boundaries, lot of uncertainties are involved. So these real world problems tend not to have a single agreed upon description. The insight here is toy problems serve as a training grounds for the real world problem. So these toy problems are used to develop and test and compare the algorithms. So once the algorithms performs well on the toy problems, we then check it on the greater scale in the real world complexity. Okay. Now, the characteristics, as per the characteristics are concerned, toy problems are not real world problems. As I told, it is generated for fun and educational purposes. Second, they are basically played on a board or paper. Okay. So the environment is completely controlled. So you don't have any kind of ambiguity there. Okay, we can write any kind of code, run experiments, measure performance. They can be converted into computer programs. Any kind of talk. We talked about two toy problems, monkey and banana, and then we talked about the vacuum cleaner world problem lastly. Now we'll be talking about the 8 puzzle problem. So they're all used as a problem solving venture for the AI techniques. Now we will go into the problem of 8 puzzle. So 8 puzzle problem is one of the most popular one in AI. So it's a very simple problem to demonstrate the concepts. So the 8 puzzle problem is used to illustrate problem solving, search techniques, state space search, heuristics algorithms. So it is also called as the sliding block puzzle. So when I say problem solving, it means how to formulate the problem computationally, how to systematically explore the possible solutions, how to represent all the possible configurations with respect to state space. When I talk about heuristics, how to make smarter and guided searches. The idea here is very simple, but it's very rich. Now, the puzzle is played on a 3 cross 3 grid. So 8 of those are occupied by the tiles numbering from 1 to 8. The rule is, the ninth square is a blank space, obviously, because there are 8 numbers. A tile that is immediately adjacent to the blank space, horizontally or vertically, you can slide the particular tile. For example, if this is your initial state, I can move tile 6 here, move tile 8 here, or move tile 5 here. So the objective of this problem is to bring to this goal state, meaning, see, it's arranged like this, 1, 2, 3, 4, 5, 6, 7, 8. So some scramble arrangement is given as the initial state and you're trying to reach this goal state. So this can be arranged in 9 factorial ways with the so many possible configurations. So now let us discuss about the components of this 8 puzzle problem. So when we formalize a problem for an AI system, we define 5 components. First one is the states. A state is a complete snapshot of the puzzle at any given moment. In the 8 puzzle problem, a state is the exact position of all 8 tiles and blank space across all 9 squares. Each unique arrangement is a unique state. So you remember there are 3,62,880 possible states. We talk about the initial state. This is the starting configuration. Any valid arrangement is considered to be as an initial state. So when we talk about the successor function, this is the function that generates all the legal next moves from a current state. From any given state, the blank can potentially move in all 4 directions. Directions that you can move your tiles are left, right, up and down. The successor function always returns a valid resulting state. Why successor? Because these are the states that immediately follow or succeed the current one. All states and their successors form the state space, the total configuration. What is this goal test? The goal test checks whether the current state matches the goal configuration. Okay. This is how the algorithm knows whether it has found the solution or not. We usually define one goal configuration. It's also possible to define other goals as well. So when we talk about the path cost, in the 8 puzzle problem, each tile moves exactly 1 position. So the cost is 1. So the total path cost equals the number of moves made to reach the goal. We prefer solutions with fewer moves. Shorter path cost means more efficient solutions. So these 5 components, state, initial state, successor function, goal test, and path cost, form the standard framework for problem formulation in AI. Now, we will go with the solution, how we solve the puzzle. Supposing if we try with a brute force approach, try all possible combinations of moves until you find the solution or the goal state. But it's extremely inefficient. Instead, AI uses something called the heuristics, an estimate of how close a given state is to the goal state. One common heuristic is the number of tiles in their correct position. We give a score of +1. This is for every correct position. A higher score means we are closer to the solution. The solution itself is a sequence of movements that transform from the initial state to the goal state. Each step is one legal slide. Okay. And that is already in its correct place. Sorry. So transition function or the successor function we defined earlier determines which tile can legally move one step. Okay. This is the goal state we have to achieve. Now, this is the state space for the 8 puzzle problem. So you can see the configuration on the left and the goal configuration on the right. Okay. However, the complete board is not here. Each intermediate step represents a legal tile movement. The AI searches through the state space using the heuristics algorithm to find the most efficient path from start to goal state. So you can see here, this is the starting position. What are the possible moves? I can move tile 6 here. That's what's done here. So the blank moves here. Now the blank is here. What is the other possibility? I can move 5 here. So if I move 5 here, this position is going to be the blank. I can move 8 here. Now this position is the blank. Out of these 3, you have to find which has a better heuristics or in how much moves it will take to reach the goal state. So already I have discussed how to solve it using Manhattan distance. You can check that. So now, supposing if this takes a minimum moves, then I can go expanding this. So already we see 1, 2, 3, 4, 5, 6, 7, 8. It should be arranged like this. Now, if I move 7 here, because here is the blank space, right? 7 here or 6 here, the blank space varies again. Again, you can see the heuristics are calculated. Here is the blank space. Now, if this is chosen again, already you can see that the movement is 1, 2, 3, 4, 5, 6. Now I have to move 7 here and 8 here. So if this is the current state, if I move 7 here, this place will become blank. And in the next move, I can move 8 here. So this will be my goal state. Okay. So this problem basically depends on the Manhattan distance or the misplacement of tiles. So we will talk about the comparison table. Supposing we are discussing here about the 4 major algorithms: breadth first, depth first, best first, and A star. Now, when you take this BFS, explores all states at the current depth before moving deeper. It checks the neighbor before going further. If you ask whether BFS is complete, yes, BFS always finds a solution. Whether it is optimal, yes. It finds the shortest path because it explores level by level. What is the time complexity? It's high because it can explore enormous number of states. We talk about the space complexity. It must explore all states and keep it in the memory. So advantages is finding the shortest path. but it requires a lot of memory. That is the more critical part you have to remember. When you talk about the DFS, whether it is complete, no, it can get stuck into a deeper paths, indefinite paths. Will it give an optimal solution? No, because leaving the shortest path, it might go deeper. Time complexity, moderate, it depends on the problem structure. When you talk about the space complexity, compared to your BFS, it's low, but it might miss the optimal solution. It uses less memory, but it may get stuck in the deeper paths. So when you talk about this best first search, it uses the heuristics to explore the next state. Whether it is complete, no. So it can be misled by a bad heuristics. Whether it is optimal, no, because of its greedy choice, does not always lead to a best path. Whether it is moderate, it's much faster than BFS in many practical cases. When we talk about the space complexity, it's also moderate. It's faster than BFS is in many cases, but does not give optimal solution. Now, when you use the A star search or the informed search, it does the evaluation function with G of n and H of n. It guarantees to find a solution. It finds the shortest and cheapest path with given heuristics. It's moderate, but the point is it needs to keep track of the paths that it visited. But the best point here is it's efficient, complete, and optimal. The key takeaway here is there is no single best algorithm in all situations. BFS guarantees the optimal solution, but it is very expensive. DFS saves memory but may not work well. Best first is fast but imperfect. A star balances everything using heuristics, so only it is widely used today in one of the applications in searching process. So the references taken are from Stuart Russell and Peter Novick, Parag Kulkarni and Elaine Rich. Thank you.